Today's lecture. In last few lectures, we have gone through different specifications related to the new standard code, that is IS 456-2000. And in the last lecture, we have gone through what are the different specification, particularly related to the deflection criteria and what is meant by effective span. And related to that, we have seen even modification factor we have gone through, what exactly that consists of. So now we'll go through the limit state method assumption. So limit state method, there are certain assumptions. So design for the limit state of collapse in flexure shall be based on the following assumptions. So we are talking about the limit state of collapse in flexure here. And the first one is the plane section normal to the axis remain plane after bending also. So plane section, suppose if you are saying this is a rectangular section and we are saying that normal to the axis remain plane after bending also. So even it would have the bending, suppose in the longitudinal section, if we just say that this section will have the bending and because of the bending, there is certain deflection. So this is called as a bending here, and in the bending we will say that this section will remain plane. So into the plane, so this would have the plane section, then maximum strain in the concrete at the outermost compression fiber. So if we just talk about the strain and stresses for this rectangular section, this is the rectangular section, and for that, if we just talk about what would be the maximum strain. So maximum strain would be occur and for the outermost compression member. So outermost compression member, it is this part. Why this one is the compression part is at the top, and while this is bottom part is the tension. So this 0.0035, this would be the maximum strain. This would be the maximum strain, and that would occur at this particular part. So this is the why, because why we say, because the loading is acting this way. So whatever loading is there, so it would act like this, and that's the reason many a times. So if this is a longitudinal section, so in that case you will have the bending like this because of the loading, and here you will have the compression part, and here you will have the tension part. So the first one, that is the plane section, normal to the axis, remain plane even after the bending. Then maximum strain, that is 0.035. So that's the first, that's the second. Now the third one, the relationship between compressive stress distribution, between the compressive stress distribution in the concrete and strain in the concrete may be assumed to be rectangle, trapezoid, parabola, or any other. So basically, if we just talk about the stress distribution, how would be the stress distribution and the strain in the concrete? So this kind of diagram will be in terms of rectangle or trapezoid or parabola or any other shape. So you will have such kind of relationship if we just talk about the distribution, stress distribution over the concrete. If we just talk about, this is your section, and what would be the stress distribution at this point, at this point, at this one. And in case you will have this neutral axis over here. If you have this neutral axis over here, so upward side, what is the stress distribution? Downward side, what would be the stress distribution? Most of the time, this will be the symmetrical. Above the neutral axis and below the neutral axis, you will have the symmetrical. So that will be seen how diagrammatically also. So continuing to the assumptions, then acceptable stress strain curve. This is a diagram. This diagram is also in the IS 456 code. So acceptable stress strain curve is this one. And for design purposes, the compressive strength of the concrete. So compressive strength you are talking about. So when we talk about, this is the stress on the y-axis, this is the strain on the x-axis. So if we just talk about the stress strain relationship for concrete, so it depends. This is for the concrete. For mild steel, it would be different, and particularly for 250 grade, this would be different. For 415, for 500, you'll have the again different relationship. Why it is so? Because mild steel, it is considered, as the name itself suggests, Fe250, that is mild steel. But when we say HYSD, high yield strength bar, or even we call it high yield strength deformed bars. So in such cases, you will have the stress relationship would be the different one uh, in in terms of or in comparison to the Fe250. So if we just talk about this compressive strength of the concrete, so shall be assumed to be 0.67 times the characteristic strength. So suppose this is the FCK. FCK, as we have covered it in the earlier lecture, that is the characteristic strength of the concrete. So characteristic strength of the concrete, suppose if you have this M20 grade concrete. So M20 grade concrete is there. And now this is your FCK. 20 would be your FCK. So in this compressive strength shall be assumed to be 0.67 times FCK. So if you just multiply 0.67 multiplied by 20, multiplied by 20. So 0.67 times FCK, that would be the maximum, or you can say that would be the assumed strength. That would be the assumed strength. So if we just calculate that 0.67 multiplied by 20, so you will get it around 13.5 or more approximately 13.4 Newton per mm square. So that's the Newton per mm square. Unit would be Newton per mm square. If we just talk about the 20 Newton per mm square. So this is 0.67 times the characteristic strength. So 0.67 times the characteristic strength would be here. Now, the partial safety factor, that is for the material concrete, we have seen the partial safety factor. Now, in earlier lectures or in the first lectures itself, first 2 or 3 lectures itself, we have seen this terminology. These terminologies are very important because we are going to use those terminologies. And yes, earlier videos link have been already posted on Google Classroom. So you'll just go through that because now we'll be directly going through this terminology. We won't go again what is meant by characteristic strength or what is this partial safety factor, because we already discussed that. What is compressive strength or what is this characteristic strength? So we won't again go through that. So we'll directly apply those terminologies. So here we will say that the partial safety factor gamma m for the concrete material, that is 1.5. We already seen that. So it shall be applied in addition to this. So if you apply that, so this is M20 and just divide it by 1.5. If you just divide it by 1.5, so that would be applicable to that. So means you got here 13.4 divided by 1.5, so you will get 8.93 Newton per mm square. So you will get, if suppose you are going to consider this M20 grade of the concrete. So acceptable stress strain curve is this one. Then what is the compressive strength? That is 0.67 times characteristic strength. Then partial safety factor is to be applied and divided to that particular value you will get. Now, so those were the basic assumptions. So those were the basic assumptions. This plane section, maximum compressive strength. Then what would be the diagram? Again, what should be the compressive strength? Then partial safety factor if applied. Now, so in these assumptions also, okay. So in these assumptions also, if we just look at this particularly, okay. So this is how the stress, as I already, as you have seen that the stress diagram or the strain diagram or the distribution of it over the concrete section would be either rectangle or parabola or trapezium, right? So if we just look at now, this is your strain diagram. As you have seen, the maximum strain, okay, maximum strain is going to be at this part, and the stress distribution, how would be the stress distribution? So if suppose this is the neutral axis, this is your neutral axis, okay, this is your neutral axis, and above that you have this stress diagram, you have this stress diagram, okay. So that is a rectangle, this part is rectangle, okay, this part is rectangle, while the remaining part is going to be parabolic. This remaining part will be the parabolic. So this is the standard one. You take any kind of rectangular section, you take any kind of rectangular section, and you have this AST here. AST, as we have seen, that these are the rectangular parts. So reinforcement bar, if you just look at here, these are going to the reinforcement part. So that is this AST you have noted down. Now, suppose this is the width of the beam. This is the effective depth. We have considered or we have seen that effective depth as well. right? Effective depth is this one, and total depth would be at the outer part. Effective depth is considered at this AST. So if you just calculate this, if you just draw this line to the center line, and if you can look at here, you will get the stress diagram. The stress diagram is only above the upper part, while the strain diagram, it is exactly symmetrical. If you just look at here, the strain diagram would be exactly symmetrical. But stress diagram is only up to the above neutral axis. Why above neutral axis? Because above neutral axis mostly, if you are talking about the compression part only, okay, compression part only. So above neutral axis, that will be taken care, that would be mostly applicable to take care of the compression. As you know that the yes concrete is very good in the compression, while the it is weaker in tension. Weaker in tension. So we have already seen that okay, compression, where will be the compression part will occur? So yes, the compression part will occur in the upper part. Compression will be at the upper. Why? Because the loading is acting like this. So that is the reason it will behave like it. It will behave. It will have certain deflection like this. And that's the reason here you will have the compression, here you will have the tension, and to take care of this tension part, you provide the AST, while the if you just calculate neutral axis, so this part will be taken care by the compression, and that's the reason this is the stress diagram. The stress diagram is like this for this compression part, and if you just see, um, so if you just see that the tension as well as the compression part, you'll have the different one. And as we have seen in the assumptions itself, what we have assumed, what are the different assumptions? This is the 0.035, that's the maximum. You will have this kind of the stress behavior or the strain behavior, and then you will also have, or you have to also consider this 0.67 times FCK divided by 1.5. Yes, if you just divide 0.67 divided by 1.5, you will get 0.45 FCK. Okay, 0.67. If you just divide it 0.67 by 1.5, just like here, so you will get 0.45. So now here, if you just look at the diagram, so here this is the maximum stress 0.45 FCK. This epsilon Cu, that is 0.0035, that is the maximum one. Okay, this is the maximum one. While if you just look at now this particularly diagram, if you just look at, this is the, as we have seen, this is the neutral axis. So what is the depth of neutral axis from the top fiber? So this is denoted by XU. XU, it is the depth of the neutral axis. So neutral axis, these are the terminologies you already that you are very good familiar with it. So neutral axis is suppose if you are considering at the location of XU, so 0.3 XU for 0.4 sorry 0.43 XU, you will have this parabolic stress distribution. Uh, Again, I'm sorry. For rectangular part, you will have this 0.43 XU, and 0.57 XU, you will have this parabolic. So 0.45 FCK, what does that mean? It means that up to this part, 0.43 XU, it would be same. But then afterwards, it just goes on decreasing, and at the neutral axis, it will become almost zero. So if you just look at this compression force and the tensile force, because you are going to provide here AST, or you can say that's the area of the steel, or you're going to provide the that particularly different reinforcement bar, and at that location you have this tensile force here, and you'll have the compression force. Yes, that would be in the opposite direction. So this is in the, if you just show in this direction, so you will have this tensile force in this direction. You'll have this in the opposite direction. So this is the basically, if you just look at this rectangular section, or specifically reinforced section, and more specifically singly reinforced section. Why singly reinforced section? Because you have provided AFC in tensile zone itself. This is your tension zone, and this is your compression zone. So when we say this is a section, right, you are going to provide your ASC, then you will say it is a reinforced section. Now you are going to provide it only in the tension zone. Yes, that is called as a singly reinforced section. That is called as a singly reinforced section. So now we'll just check here. So in these assumptions, this design stress block, area of the stress block is considered as we have seen in the diagram, that is 0.36 times FCK into XU. XU is the depth of the neutral axis, FCK it is the characteristic strength. Now, a depth of the compression force or compressive force from the extreme fiber, as you have seen, that is 0.42 XU. 0.42 XU. But yes, we already seen this. FCK is the characteristic strength, or more specifically, characteristic compressive strength of the concrete. XU, it is the depth of neutral axis. Now, tensile strength of the concrete is ignored. Why tensile strength of the concrete is ignored? Because in the concrete, you have the tensile strength maximum up to 8 to 10%. Maximum up to 8 to 10%. So that's why it is ignored. So stresses in the reinforcement are derived from the representative stress strain curve, and this typical curve, as we have seen, design purposes and partial safety factor gamma m for reinforcement. For reinforcement, it is 1.15, because this is steel. As we have seen here, for the concrete, it is 1.5, but for the steel or for the reinforcement, that is 1.15. So because this is the partial safety factor for the material. And then a maximum strain in the tension reinforcement at the failure shall not be less than, this is the formula here, which is already given in IS code. So which, these are the part of the assumptions. So these are the part of the assumptions. We are looking at the LSM. LSM, that is the limit state method, and what are the different assumptions, or on which basis we are going to design. We have not yet started the design. We have not even started the design, but just we are going through what are the different notation, what are the different parameters, and what exactly Indian Standard Code means. So Indian Standard Code, that code itself suggests whatever the things are there, accordingly we have to follow. So it just says that maximum strain in the tension reinforcement at failure shall not be less than Fy divided by 1.15 ES. What is ES? Modulus of elasticity of steel. Fy, characteristic strength of steel, and plus 0.002. Plus 0.002 from where that occurs? It occurs from this stress strain relationship. Here this is 0.002, you have this parabolic curve, and then up to the 0.0035, you have this as the just almost a straight line, or you have the stress relationship, it is almost linear. But while it is up to that 0.002, you have parabolic curve. This is the parabolic curve. This is the parabolic curve. So we have seen here that this is the maximum, or it should not be less than 1 FR by 1.15 ES plus 0.002. So if you now look at what are the different properties of singly reinforced section. So we have seen section, we have seen if it is reinforced, then that is called as a reinforced section. But if it is only reinforced in the compression, in the tension part and not in the compression part, then that is called as a singly reinforced section. So we have already seen that singly reinforced section. WSM part is not here, but this is because if you have seen it in the fourth semester, what is WSM, so that you're well aware of it. So the basically the beams, you know that the bending occurs. Bending is also called as a flexure. Always remember this, bending is also called as a flexure. Why? Because why this occur, bending or flexure, why does that occur? Because your that particularly beam or the section is or have that external load or the lateral load, and that's the reason that this kind of singly reinforced section, what are the different stress distribution and strain distribution on that singly reinforced section is very important. Where exactly this particularly maximum value is there, where exactly the maximum value is, and where you have the minimum one. So this is the diagram. Mostly this is the generalized diagram, how the stress distribution is, and based on this, basically based on this, you will have to calculate the different parameters, or there are different formulae related to this, that based on what is the strain or what is the stress and how this particularly at which location you got your rectangular section, or what location you have this parabolic section. This compression force, where exactly it is acting at 0.42 XU, while this is the tensile zone. This is tensile zone is acting at this location. So depending on this part, depending upon the maximum compression or maximum stress on the compression part, and this epsilon Cu maximum strain. So depending on that, so you'll have to calculate the things, or there are certain formulae you have to apply. So based on that, these are actually already calculated parts. And if you just see that the compression force will act at the CG of the concrete stress diagram, right? So depth of compressive force, that is Cu or Y bar, how this 0.42 XU, as we have seen, we already covered that this is 0.42 XU. But how that occur? If you just look at this, F is known to you, F equals to 0.45 times FCK. Now you just take the moment of that particularly forces related to the that stress distribution diagram. On the stress distribution diagram, if you just look at, and based on it, so you'll have to, you will get here the first part, and then this is the second part, and This is the first one, and this is the second part. So that is simply you have to take the moment, and based on that moment, you will get this y bar, that is 0.42 x. So uh, from here, you will be able to understand basically how that particularly thing is to be calculated. So anyhow, what exactly important? This is the major part. This is important that yes, this CU or this compressive force, the depth of that, or where does that occur? So it occurs at 0.42 XU, this below compression edge. And how that occurs? So with the help of this moment, taking moment about that part, so you will be able to calculate it. But what is more important? This is more important here, and this you can see, or you can just check how that particular thing is available. And similarly, once you got this compressive force, so once you got this compressive force, total compressive force, as you know, that is Cu, and based on that Cu, that is, you know, that area of the stress block, if you just multiply it with the width, so you will get the total compressive force. So um, it is simple. If you just consider that the strain part, so using the strain part and using the stress part, how or what would be the or this compression force, total compression force, basically what is the value of it? Total value, what is the total value of it? So this total value is 0.36 times FCK into XU into width of the beam. So it is again very simple. Area of the stress block, we are considering that area of rectangle plus area of parabola. So area of rectangle plus area of parabola with the help of this diagram. So as you have seen, with the help of this diagram or with the help of these different notations, you have to just simply calculate this part, taking the moment, taking the sum. This is what you will get. So uh, so that is you will get. And we are more interested what is the value of Cu, what is the value of Tu here. And once we got that, and based on it, you will we will get the certain formulae, and based on that certain formula, then we'll go for calculation, or then whatever the designing problems will be there, that will be considering. So first of all, you have to understand this is the complete diagram, more specifically how the stress diagram is there, how the strain diagram is there, where is exactly rectangular part is located, and how this parabola part is there, and where exactly the Cu is located, and based on that, how you will get the 0.42 XU, or how you will get these values. Once you got that, this XU or this Cu and this Cu means compression force and tensile force will be all calculated. Okay, so we'll go step by step. We have not yet started it, and this particularly how exactly these forces are going to be calculated. You can go ahead that because these are the standard one, and we'll be not looking much in detail for that. So we'll stop here, and you can just mark your attendance on the Google Classroom, and also go through the earlier lecture videos and whatever the upcoming lectures will be there. So I'll just again give you the link of it on the Google Classroom itself. Okay, so thank you.